Great movie, The Martian. I hope you've seen it. But at the end of the movie, spoiler alert here, Matt Damon's character has to get off Mars at faster than the ship was designed. And so one of the things they do is they reduce the mass in the Mars ascent vehicle to get him off. Anyway, here's my version of the Mars ascent vehicle in the last few moments of that movie. Well, of course, the Mars ascent vehicle is sitting on the surface of Mars, which doesn't have a strong gravitational force, but it has some. And that's going to result in a weight force because of the mass of the rocket ship. And in fact, most of the mass of that Mars ascent vehicle, most of the mass of any rocket ship that launches off the surface of the Earth, the overwhelming component of that mass is fuel. So that weight force is made up by a whole lot of fuel. But of course, once you start burning that fuel, and you burn that fuel generally, certainly in this movie here, in a chemical reaction, igniting it, heating those gases, forcing them out through a nozzle, which means you're accelerating them. You're putting a force on these exhaust gases, a very strong force to accelerate them and to change their momentum. And of course, the law of conservation of momentum means if you've changed the momentum of the exhaust gases going downwards, that's going to result in a change in momentum of the rocket ship upwards in order for momentum to be conserved. Or if you like it, in terms of Newton's third law of motion, for every action, there's an equal and opposite reaction. So as you push and force down these these exhaust gases out through the nozzle of your rocket, you're pushing them downwards, they're going to be pushing upwards on you, and they're going to give rise to this, the thrust force. But it's not the thrust force that accelerates the rocket ship, it's actually the net force. And as you get faster and faster, well, to start with, this is going to be 0 on the launch pad, but it's going to increase with velocity. And that's going to give rise to the net force. And the net force, this one here in red, is actually the force that causes the acceleration according to Newton's second law, F equals ma, or the acceleration of a rocket ship is the force, which is always the net force, divided by the mass of the object. Now, as I said, the fuel is the overwhelming contributor to the mass of the whole spacecraft. And as you're burning that at enormous rates. The mass of your rocket ship is decreasing very, very significantly. It's much more, you don't notice it much in a car. You don't notice that a car accelerates better with an empty fuel tank or near empty fuel tank compared to a full one, because the mass of the fuel tank is kind of not that significant in terms of the mass of a 2,000 kilogram car, and you might have 100 kilograms or something of fuel. But in a rocket ship, it's the other way around. It's massively fuel. So the first effect that has is it actually reduces the size of the weight force, because weight is mass times the gravitational field strength. That's a significant but a reasonably minor effect, but what that does is it increases the size of the net force. So we have an increase in the size of the net force, which means we're going to have an increase in the size of the acceleration. But actually the most significant effect is this mass here, the reduction in the mass. That mass goes down very, very significantly to a small percentage of what the rocket ship actually weighed on the launch pad before it took off. And that is what results in a massive increase in acceleration. So the rocket gets faster and faster at a faster and faster rate of acceleration because the mass goes down. So our net force increases, that has an effect, absolutely. But even with the same net force, the reduction in mass means you're going to get more acceleration of the rocket ship. And so you see poor old, the character played by Matt Damon, it was at the very, very end of the rocket launch that he passed out and his rib got broken. And that's actually as it would be because it's that last few seconds of fuel when you've burnt almost all of your fuel, the mass is now at a minimum, but the rocket motors are still producing their maximum amount of thrust, and that's when you're going to get the maximum amount of acceleration. What happens? What else can affect that? Well, of course, drag can affect it as well. So as the rocket ship is getting faster and faster and faster, there would be a reduction in an increase in the amount of drag, which would slightly reduce the amount of net force. But that's, remember, completely overwhelmed by the loss of mass. But of course, then as you get higher and higher and higher, two more things happen to increase acceleration. First of all, even though you're getting faster, drag actually starts to reduce because you're getting in past the edge of the atmosphere until you get beyond the atmosphere and there's no atmospheric drag at all. And even on Mars, where it's a very, very thin atmosphere, it still does create some drag, and as you get higher and higher, that drag becomes less and less and less. And the other effect of becoming at a higher altitude is it reduces the size of the gravitational field strength, which is going to reduce the weight force as well. So those two factors combine to actually increase, yet again, the size of the net force. So you've got all these things happening. Overwhelmingly, you've got this loss of mass of fuel, which is going to increase the acceleration of the rocket ship, even with the same net force. But overall, the net force is increasing because you're losing weight force, because you're losing mass. The weight force is getting less also because the G the acceleration due to gravity at that altitude is less, and also because as you get higher and higher, the amount of drag on the rocket ship is less. And so all those things mean that when you look at the acceleration of a rocket ship, it looks something like this until it gets to the point where it's quite dangerous. And the reason it was dangerous for the character in the movie is because that actually reduced a whole lot of mass off this rocket ship in terms of nose cones and bits and pieces they didn't need in order to get it to a higher altitude, which means the acceleration would have had to been greater because it's only got a certain period of time that the rocket motors burn for. So it would have got to a point where, yeah, it was beyond 10G is the point where you're really going to start to have significant effects on human beings. So any kind of real rocket has mechanisms to reduce the amount of acceleration, to keep that acceleration, and therefore the G-force on the astronauts below a minimum. But G-force on the astronauts is another video, so we'll leave that for then. So there's a bunch of reasons then. Overwhelmingly, the loss of mass means that A equals F on M, a great increase in acceleration. The loss of mass also reduces the weight force. Also, you've got a thinning atmosphere. Also, you've got a reducing G-force, and all of those things conspire to massively increase the acceleration of a rocket ship during the time of its launch.